let me just summarize a few of the things we saw yesterday. We did go through quite a bit of material, which was mostly review, but one of the things we reminded ourselves was that string theory, our definition of string theory is a perturbative definition, where we consider the scattering of strings by saying that we should sum over different topologies. We sum over all histories, like we always do in quantum mechanics. So we sum over all ways we can join three strings, and we can join them to leading order in a pair of pants topology, which is what's called a sphere with just three insertions. And then we have genus 1, genus 2, and so on and so forth. And we weight these guys with some power of the string coupling, which, as we said, it's not really up to us. It's the only thing we can do. For example, even in this simple example, imagine I break this pair of pants with one loop, and I cut it like this into three pair of pants, you see. So because this pair of pants can be cut into three, it better be that the power of this diagram to be the cube of the power of this one. And indeed, it works. You see, G string appears there, G string cube, and it had to be. It had to be because we can break this pair of pants into three pair of pants. Okay, but more precisely, what do we do? Well, we sum over surfaces of the given genus, and for each genus, we integrate over all possible shapes. So we sum over topology, and then given some topology, we integrate over geometry. And we sum over all surfaces for a given topology. And what's the weight? Well, here the second constant appears, the tension, the string tension. The string tension suppresses the weights of various string configurations. And typically, big string tension is when things are simpler, and small string tensions is when things are harder. Harder in the sense that if the tension is small, then I have no way out. I really have to sum over all possible surfaces. But if the tension is large, I might expect some simplification, that perhaps the strings shrink and something simple happens. So there are these two constants, the string tension and the string coupling. We also saw that, in fact, in practice, there's only the string tension, because the string coupling I can absorb, or I can think of, as just saying that my dilaton has some expectation value, right? Because if the dilaton has some constant parts, the integration of a constant times the Ricci scalar over some surface gives exactly some number times this combination here. So we can even just say that string theory, it's all about the string tension, which is 1 over the string length square. Then we made an important claim. We said that if you have a theory with a large n expansion, where graphs organize themselves also as an expansion over topologies, it looks like we are tempted to say that large n gauge theories are string theories. And indeed, we saw, for example, that if we consider a correlation function of three composite operators of this sort, trace of phi to the j, we saw that each operator I could draw like this. So this is a picture of one of the operators here, which looks like, again, a tube that I insert here, a circle. So I insert a string there. And I consider three strings, you see, three circles. And then if I sum over all diagrams, it looks like I'm discretizing, I'm triangulating some kind of surface, right? The more graphs I draw, the more it looks like a smooth discretization. If I continue drawing more and more and more, at some point it really looks like I'm describing a smooth surface of some string. So this, in 3D, would be exactly like some triangulation of this surface here. And we should sum over all diagrams, but we saw that they organize in the following way. First, you select some topology. You tell me I will draw diagrams that I can draw on a sphere or on a plane. And then, for that topology, you do sum over all possible Feynman diagrams and compute them. But different topologies come with different power of n. So the most important topologies are the spheres, then the genus 1, genus 2, genus and so on. So it looks like the analog of summing over surfaces is played by summing over all diagrams of a given genus, and the analog of summing over genus is summing over genus. Okay? So this leads to the idea that large n gauge theories we should be able to recast them as string theories. And if we could do, you see the promise, it's tough to do, but the payoff is great. Because imagine you want to describe some 4-dimensional gauge theory like QCD. If you could translate it into a string theory is simpler. It's 2-dimensional. You would have to tame the fluctuations of this two-dimensional string, but it is much simpler to do path integrals over two-dimensional fields than four-dimensional or five-dimensional, six-dimensional. Okay? So we should be motivated to do it, because if we succeed, as we said, the payoff is big. Okay, so just to practice a little bit, let's remind ourselves. So here are, for example, a few vacuum diagrams that would contribute to the free energy, say. So here are a few vacuum diagrams that we would compute for this scalar theory. So this would be a vertex phi cube, and this would be a scalar-to-scalar propagator. And you see that as you draw, there are some diagrams, like you sum over all these diagrams in this first line that can be drawn on a sphere. And then you sum over all these diagrams here that can be drawn on a torus. And then, for example, I wrote here one that you can only draw on a torus with genus 2. So let's, for example, work out, just to practice once, say, this diagram here, the scaling of this diagram. Okay, and let's check that it works out, that it should, this is what it is. So let's see, how many propagators we have? So can someone tell me how many propagators? Let's see, 5. 1, 2, 3, 4, 5. 5 propagators. And each propagator came with a factor of G Young-Mills to the G Young-Mills, right? Because there was 1 over G Young-Mills before the kinetic term. So G Young-Mills is lambda over n to the power 5. How many vertices? 3 vertices, 1, 2, 3. Each vertex came with a factor of 1 over G Young-Mills, so lambda over n cube. And how many powers of n? How many loops of color do I have? 4, right? 1, 2, 3, and the outer one, 4. So n to the 4. So this gives n to the power minus 2, I guess, right? So 5, 7 minus 5, 2, yeah? N squared times some power of lambda, which in this case is lambda squared. Okay? But what's important is this n squared, that indeed it works out. If I plug there n equal to 0 and g equal to 0, I get a power of n squared as it should be. Okay? Okay, so you can easily work out that it's always like this. So this one here, for example, will also be of order n squared, but probably just lambda, not lambda squared. So 1, 2, 3, 1, 2, yeah, but order lambda. So this one is n squared times lambda. Okay? Okay. So both of order n squared, but different powers of lambda. I have to sum this guy plus the other one plus etc. plus etc. Okay. So I would like now to make a few more comments about why this analogy indeed looks reasonable, why it looks reasonable to think of a large n gauge theory as a string theory. So I would like to give some further flesh to this idea. But any question here before we start? Yes?
Can we also have genus half or half equal?
No, you always have
Open this
Yes, yes, if you do in the same sense as here. So the question, so for example, this n, it's like having a boundary, right?
Yes.
So you can generate this n by saying that I add some halves to the genus G. So that's fine, that's also, that's true. If I consider this surface here, it has 3 boundaries if I want. I have 3 vertex operators, so which I can think as 3 boundaries. So, and indeed, the counting works out in that way. And if you were to consider disks topologies, which here we always have closed surfaces, indeed you would get the corresponding Euler characteristic for an open surface.
we need those boundaries or not, or we can just use this formulation.
We definitely sometimes in theories need boundaries, yeah.
Okay.
And I will explain in a minute. I will give an example in a minute. So the question is, right now, it looks like I'm considering an operator, trace of phi to the n. And trace of phi to the n is a closed object. Why is it closed? Because I have a bunch of phis, and they are in a trace, which is a cyclic object. So this is about closed strings. Trace of phi to the j, you put a closed string. Okay? So here, each of these operators, and each in this picture, And also in this picture, this stands for here putting a closed string. But we also have open strings. So, and indeed, we will see that the closed strings are not more important than open strings. I just chose here to start with closed strings, but soon open strings will also appear. More questions? Yes?
Is there anything at this stage that suggests that what you have inside the sum over diagrams and painted below that should be the same?
Sorry, can you repeat? If I can map this thing to this thing directly? No, that's very, very hard. So let me make a comment here, so related to that question. So this part here is easy for lambda very small, because if lambda is very small, we typically want the simplest diagrams with 1 loop, 2 loops. You see there, for example, that first diagram is lambda. That other diagram that has more loops is lambda squared. So these diagrams are easy when lambda is very small, when we do just 1 loop, maybe 2 loops, and so on. So after we draw the diagrams, but then consider very simple diagrams. This part is easy for very large tension. And typically, the coupling will be related to the tension. This wiggly doesn't mean proportional, because there can be powers and so on in this relation. But the basic picture is the bigger the Tooth coupling, the bigger the string tension, because the intuition is that the bigger the Tooth coupling, the denser these graphs become, and the more I'm approaching this limit of a classical string, the more I get of a smooth classical string description. Whereas if the coupling is very small, then my surface does not look at all like a surface yet, because I only have very simple graphs. So it's more like a fluffy string with a very quantum one that does not look like a reasonable description. So typically, you cannot make a direct connection between these sides, because when this one is easy, this is very hard, and when this is hard, this is very easy. And that's why typically checking these dualities that we will have is very tricky and very hard. So it's very hard to start being rigorous, drawing all the graphs, taking a limit, and getting to a string theory.
So far, the conjecture is just based on the fact that you have something that looks similar on the outside.
Yeah, that's it. As we will see, so the goal of these first 3 lectures is to provide many crappy evidences for a conjecture, but many. And the intersection or the union of all of them, I think you will all be convinced that this correspondence should be true. So we have to provide evidence. Why should such dualities exist? But their power lies in the fact that they are precise. It's precisely because it's not trivial to show them that they are so powerful. Yes?
So in particular, it's totally unclear, for example, how, say, as you said, when we have a 4D QCD, how you translate to like a much simpler like sigma model in the...
Absolutely. Okay. No one has any idea for what is the sigma model describing QCD, for example. But I mean, okay. I think it should exist. Very good. So now let's see. Let's continue studying a little bit this large n limit to see what it is telling us. So here I should write something important here, actually. This is the connected part. Actually, in this case, it doesn't matter much. But this estimate, what's written here is when you draw connected correlators. Okay? So let's make a few comments now. So the first comment is trivial. It's just that the planar 2-point function is n independent. Okay? Indeed, if I take genus 0 and n equals to 2, there's no power of n. And also here, because it's the same formula, if I take genus 0 and n equals 2, so this is like just the propagator. This is the analog of the propagator. So I just have a tube, and this is n independent. While the planar 3-point function is of order 1 over n, which we identify with a string couple. Okay? So this is fine. So it's telling us that we have just propagator well normalized, and then the 3-point function that measures the interaction is of order G string. Now, so this is a simple comment. Now a slightly less trivial one is what happens if I consider the correlation function of 4 operators. Okay? Now, notice something. If you consider the correlation function of 4 operators, right, there are 2 possibilities. I can have a disconnected contribution where I just connect OO with OO. And by sum, I mean that I can connect this with this and this with this, or do the other weak contractions. Or I can have the connected contribution. Okay? In pictures, this first one I would draw as a string that propagates, and I'm putting it wiggly, 2 strings that propagate freely, and I'm putting it wiggly to indicate that we do sum over their surfaces, but the topology is just planar. Okay, and here we will do, okay. And here, we will be summing over a connected interaction where they are all connected. Okay? Well, and what is the, well, this thing here, they are n independent, the 2-point functions. Whereas the connected contribution, you see, if you plug n equals to 4 and genus 0 there, it's of order 1 over n squared. Which, once more, has to be, I'm always emphasizing this, because we can cut it into 2 pair of pants, and each pair of pants is a G string, so it has to be G string squared. Okay? So we see something interesting, that in large N theories, we are describing weakly interacting strings. We are describing strings that to leading order like to propagate, then they interact a little bit, then they interact a little bit more, and so on. So large N means free strings. This word free is dangerous because people often think free is trivial. It's not trivial anyway. By free, I mean that the strings don't interact with each other, or when they interact, it's just they interact with the simplest possible topology. I might consider this topology, but not the 1 over n to correction, which will be the torus 1. But it doesn't mean it's trivial. For each topology, I still sum over all possible shapes, so it's still non-trivial evolution and non-trivial interaction, even when I consider leading order. But free in the sense that I don't need to consider very complicated joining, merging, splitting, and so on if I'm at large n. Those processes are suppressed. Okay? So, okay.
When you draw the diagram, like, do we have to sum over all different genus?
Yes, yes. We would also sum over, so this would be like the leading part, the planar part, plus higher genus. And that's even more suppressed.
Like up to here, like why the interaction between strings are not relevant to the arc for me it is not so clear.
No, all I'm saying is that this term here, for example, is dominant over this. This is 1 over n squared, this is order 1.
Oh,
You see? So the strings prefer to propagate freely rather than interact with each other in a connected way. Right? And this diagram, and in the higher genus, for example, there would be this one here, which would be of order 1 over n to the 4. So it's even more suppressed. So typically, you can consider just the disconnect and perhaps the first correction, but you don't need to go and start studying many interactions if the n is large. Okay? So, intuitively, how would we describe, so an operator O, so we see that O, defined as trace of phi to the j, describes a single closed string So we could imagine what kind of operator we would do to describe inserting at a given point many closed strings. Right? Suppose I want to create a state that produces me 5 strings, not just 1 string. Okay? Any guess?
Just O to the side.
Sorry?
O to the side.
Exactly. So for example, I could consider an operator O tilde that would be a product over n of trace of phi to the power ji, always at the same point x. But I just consider many single trace operators. And indeed, if I were to consider O tilde of x with O tilde of y, this would be to leading order, so approximately equal. To leading order, each trace just talks to one another. So it would be approximately the product from I equal 1 up to n of the correlation OI of x, OI of y, where OI is that operator there, which would be 1 over x minus y. So if each correlation function is that of a conformal theory, say, so here I'm doing, say, in a CFT, because we'll see this is the most relevant case, then each of them is a power law behavior with dimension delta I, and what I would get here is sum over delta I of the various operators. Okay? So this is in a CFT. If it's not in a CFT, I would just write the product of the correlators of each of the operators, disconnected. Okay? But what I want to point out here is that these operators would have some dimension, which would be the sum of the dimensions of each constituent, and then there would be corrections that we are not considering of order 1 over n squared. But all I want to say is that if you take many strings together, to leading order, they behave just like a multi-particle string state, where I just add up the various constituents. And then there are corrections, which are like binding energy or gravitational attraction between the various strings, definitely. But to leading order, we have, when n is very large, we have this notion of various strings. So we have a Fock space, which is the analog of the multi-string Fock space. Okay. So that's how we think of these correspondences, that we have a bunch of operators, they generate these closed strings, and if we put many of them, we are dealing with many strings, and they are approximately free, so that it makes sense to talk about 1 string, 2 strings, 3 strings, and so on. Okay. So now, I would like to remind you a little bit and to emphasize a little bit this duality between open and closed strings. Okay, so let's draw pictures and try to yes?
When you say free strings, the action that describes them is still the polygon action plus some other terms, and stuff like that?
Yeah. No, by free, I just mean free from the point of view of G string, not free from the point of view of string tension. The string is still a very non-trivial conformal field theory. It can be strongly coupled. To describe the propagation at a fixed genus is very complicated. The string vibrates, and so on. But the only point is that we don't need to consider genus with many, many holes, because those are very small.
So the action is still the same?
The action is still the same, and by no means it means it's trivial. A free string is not like a free quantum field theory. Free quantum field theory is trivial. Just with contractions, we are done. Right? There's nothing to do. By free string, we must be careful. Free string just means a string that where strings don't like to join and split, but their propagation is still very non-trivial. And their cubic vertex is still very non-trivial, and so on. Okay. So, open versus closed. So I'd like to discuss a few aspects of these cartoons at large n and whether they describe open strings or closed strings or whatever. Okay? So let's start with so the basic, I remind you of this picture that we drew before, where we said, well, if I have a closed string that is being emitted by a brain and absorbed by another brain, that depending on my point of view, I could think that this is either a closed string or an open string. attached between the two branes and going around. And indeed, I can describe this as an open string stretching between this brane and going around, or as a closed string being emitted from one brane to the other. Okay? Good. So let me see what I want to do. So let's discuss a little bit more about this open closed string duality. So first, let me remind you, related to the question that we had before, that a gluon we describe by a double line notation. Okay, it's a propagator like phi, it's a matrix n by n. Okay, but the quark we describe by a single line. A quark is just a vector transforming the fundamental of SUN. It has one index, it doesn't have two indices like the gluon, right? And an anti-quark, well, it has the index down instead of up, so it would be drawn like a picture with an arrow in the opposite direction. Okay? So let's consider a few quantities in QCD that sometimes involve gluons, sometimes involve quarks, and let's see a bit what kind of pictures we would draw. So the first one, let's consider trace of F to the J with trace of F to the J. So why would we consider such objects in QCD? Let's even go back one step. Because these objects are what are called composite, gauge invariant operators. You see that in Young-Mills, asking what's the correlation function of 3 A mu's doesn't make sense because A mu is not gauge invariant, right? So A mu is not gauge invariant, it transforms as something like that, right? In the language of forms without indices, it will be like this. So A is not good, F is better. But F is also not gauge invariant. F also transforms, but in a simpler way. Right? Under gauge transformation, F still transforms. But trace of F to the power n is perfect. So if you want an operator which is local and gauge invariant, this is how we construct it. That's why we take trace of operators in large N gauge theories, why we like this single trace operator so much. So these operators are really gauge invariant, and they are good observables in my theory. It makes sense to study correlation function of these operators. Okay? While it's not really physically meaningful to study correlation function of A or F because they are not gauge invariant. Okay? Now, in a theory like the one we described yesterday, this is gauge theory, this quantum field theory for the scalars, I did not tell you whether this was a quantum field theory or a gauge theory. I did not tell you, do the scalars transform or not? So in that theory with the scalars, you would think that perhaps I should also be able to consider correlation functions, not necessarily of this trace of phi to the j, but other quantities. And there would be nothing wrong with them, indeed. So now it depends. If I gauge my theory, if I replace derivatives in the action by covariant derivatives, then phi would also transform like f, and this would be the only good observables. Okay? But if the theory is not a gauge theory, then I could a priori also consider other objects. Now, if the theory is not a gauge theory, it means that there is some global symmetry. So it means that the string theory that I would get would have a global symmetry. So I remind that a gauge symmetry is a gauge redundancy. A gauge symmetry is not a symmetry, it's just a redundancy of our formalism. But a symmetry, a global symmetry, is a symmetry. It has consequences, it has global charges, it has conservation laws. Right? So the action I wrote, there is an important difference between in the action I wrote between derivatives versus covariant derivatives. If I use covariant derivatives, then I should only consider gauge invariant operators. Then phi transforms in this way, and then I should consider only traces. But if I consider usual derivatives, then my objects have some global symmetry. That symmetry is a conservation, it's a symmetry. It generates conservation laws, and I can write other kind of observables. Now, if such symmetry is there, it would be inherited by the dual string description, and you would have a theory of string theory with a global symmetry, right? In particular, when we take the low energy limit, we would have gravity, given by gravitons, with a global symmetry. Okay? However, in physics, we believe that gravity cannot have global symmetries. So there is a general argument that says that gravity cannot have global symmetries. And the basic idea is that suppose there is some global symmetry that allows me to consider, and I consider some object with a huge amount of that global symmetry. So for example, there's a symmetry that is distinguished between red and blue, and I consider a huge red object. And I want to say that this object is conserved. So I put a lot of global charge, and I put so much that I form a black hole. But when I form a black hole, black holes have no hair in GR. So the only thing that characterizes the black hole is the mass of the black hole. So now I lost information about whether I created it with a lot of charge or not. And now the black hole evaporates by Hawking radiation, and I started with a huge charge, and now I have no charge. So what GR did was it broke the symmetry. So GR breaks and violates global symmetries. So there are no way of putting global symmetries in GR. Okay, this is a common law thing related to black hole physics, that you cannot put global symmetries. And that is why, when we consider these large N theories, we should consider gauge theories, and not just regular large N theories. This is hand waving, but I think, but the truth is that we don't know of any theory with a dual which has a large N, but which is not a gauge theory. Again, precisely because if it were, because you see there is a big difference between being a gauge symmetry or being a global symmetry. When you have, say, a black hole with charge, and it's associated to a gauge symmetry like electromagnetism, it means that you have the photons that can radiate away. But if you have a global charge, which is just like you associate some quantum number and that quantum number is conserved and there's no way you can radiate it away, then you just say that, well, I just have 1 million units of, say, baryon number. I put but that is going to be lost under gravity evolution, so you should not have global symmetries. Okay. Okay, so this was a detour that told us, okay, QCD, it's good. QCD is we have a gauge symmetry, and these operators are perfect. They are gauge invariant, local, observable, so they are the good observables of a theory with a large N limit. So we could consider correlation functions of these objects, and correlation functions of these objects, as we said, they look like a cylinder where I consider a correlation function, and I'm uniting. This would be the case where I have trace of f to the 4. I have a string on one side and a string on the other side, and I am just uniting the propagators and summing over all possible loops here and here and here. And this looks very much like a closed string, going here. Okay? But of course, I can think from this point of view, and from this point of view, it looks more like an open string. It looks more like I'm describing some kind of open string that is rotating around. But okay, for now it is just a cartoon. But let's consider other examples where this open strings is the most natural one rather than the closed strings. Let's consider, now this is one observable, and the second observable that we could consider in QCD would be gluon scattering amplitudes. So what's the picture we would draw for a gluon scattering amplitude? For a gluon scattering amplitude, we will draw something like this. Okay? Which means that we consider now correlation functions of a mu, exactly what I said we should not do. But why can we do it? Because in scattering amplitudes, we take the operators to infinity. So at infinity, the gauge symmetry becomes just the global part of the gauge symmetry, and it's fine to consider correlation functions of operators provided we prepare them at infinity. Okay? That's why we can consider correlation functions of gluons. Okay? So we can consider them, and what do they correspond to in terms of graphs? They correspond now to drawing these graphs, where now I have some gluons with open indices in the external legs. And then I draw here some kind of diagrams of things that this could be one graph. Another graph that could be simpler perhaps would be just this one, for example. Plus, etc. Okay? So we'll draw all these possible graphs. Here is one planar graph, here's another non-planar graph, and there are also non-planar graphs that we could draw, but these ones are the planar ones first. Okay, so how do we think of what's the string cartoon that I associate to this picture now? Well, there are various pictures, but let's first remember what's an open string. So an open string has two endpoints, one endpoint here and another endpoint here. And endpoints of strings, they need to end on some place, and the objects where strings end are called d-branes. That's the definition. It's where a string ends, it's a d-brane. So suppose I put a stack of d-branes, and I put a few d-branes on top of, at the same position, on top of each other. Okay, so I put a bunch, for example, here I'm drawing 3 on top of each other. Okay? And now, when I say this is ending on the brane, I should give it an index to say on which brane is it ending. So I put an index I, and I put an index j, which tells me on which brane it ends. Okay? So now, if I have a string moving, an open string moving, the way to draw a string, a string that is moving, is by drawing the two lines and saying in which brane this is and in which brane this is, the endpoints of the string. Okay? And this is exactly how we do it in a large N theory. So this now starts to make contact with the pictures we are drawing in a large N theory. Okay? So now we see what's happening here. So let's try to draw a picture for what's happening here. Okay? Yes?
How do I get the arrows from that picture of this open string? Or like, how do I know how to assign arrows there?
Can I postpone that question? I mean, the endpoints, they are charged, and you really should think of a string as being going from a quark to an antiquark, which have some opposite charge, and the full object is neutral. Anyway, this is what's called the Shan pattern factors. Was it covered in string theory? No? Anyway, in string theory, open strings have these indices I and j associated to which brane they are. So then this picture here now becomes a bit more clear what's going on here. So let's suppose I try to draw a picture corresponding to this process here. So the beginning here, or maybe even this part here. So let's try to draw a picture for what's happening there. Okay. So what is happening there? So what we have is the following. So we have a string. We start with two open strings, and one was on brane I and one was on brane j. And then we had another string where one endpoint was on brane j and the other was on brane k. So let's write these indices here. Let this line correspond to ending on brane I, this brane j, and this brane k. And then as time evolved, so this would be time, what happened? Well, the strings got closer. And eventually the endpoints touched on the J on the middle. As they touched, they left the brain. Okay? And then I add a single string which goes from index I to index K. So this is the picture corresponding to this interaction here. Okay? Two strings were moving and they became a single string. Okay? Is it clear? So how would we draw the full process there? Well, let me try. I'm not sure if I'll be able to, but let me try to draw what's happening. So I'll draw a brain. Okay, this is a stack of brains. And now I'll try to draw some kind of picture where I say that I start with some open strings here. So you see, there are some open strings that became a single open string. Then this open string splits in two open strings. How does this splitting happen? The opposite mechanism. Now this tip of the string goes to the bottom, touches some brain. It doesn't need to be the same as it was before, some other brain L, and it splits into two. Right? So it creates a new index here, L, whereas this index here in the beginning was J. Right? It touches the end and splits into two. Okay? Then these two open strings evolve. Okay? And then something happened to them. Here there was some interaction with another open string. And then there was a splitting into another open string here. And it went to another open string here. So this is roughly the picture that happened here. Okay? But now, someone else could have a different description of, say, this middle part here. So now so this is what it is. But now someone else could say that something else happened here. Another person could say that what happened here was that I had 5 open strings coming in, right? And what happened at some point, now I'm seeing it from above, was that the brain created a closed string and emitted this closed string from itself. Okay, so this would be a closed string. Because indeed, if I cut the string here, what I see here, if I cut it, would be you see that this line here. So I can draw this line, you see. This will be going like this. So I can say that my brain emitted a closed string. Okay? So to make it more exaggerated, I would draw a picture like this, where I say that I have a 5-point amplitude. There would be normally an open string here, open strings. But what happened was that here a closed string was emitted, and it interacted with this open string. You see, it got emitted from the blackboard and interacted. So now, how do we describe it? So can we describe it here as a closed string, or going around as an open string, like we did in the beginning? And the answer is, we can do both, whatever, up to you. Just choose. It's the same thing. It's the same description. There is no way of distinguishing. I mean, it really is the same thing. And you can indeed choose to be different. And this is the realization of this open-closed string duality. So the simplest possible thing would be if I just draw, say, a double line notation like this. What is this double line graph representing? How do you think of this double line graph? Well, there are two ways of thinking about it, as we said before. Either an open string here. It's an open string that goes around this circle. Or it's a closed string that got emitted from the inner radius and went to the outer radius. Right? Or a closed string here. And this is nothing but the analog of the first cartoon that we draw there with the two brains. And the first string and the closed string, the inner line was at brain I and the outer line was at brain J. So it went exactly from one brain to the other, exactly like in the cartoon on the top. Okay? Okay, this is second example. Third example would be the quark-anti-quark potential. If I want to study how quarks and antiquarks attract, and see confinement, for example, and see that there is a linear potential between the quark and the antiquark. So now what do I want to do here in this third example? In this third example, I want to draw a quark. I want to draw an antiquark. And I want to draw all possible interactions between the quark and the antiquark by exchanging of gluons. So how do we do? Well, let's start drawing. So they can exchange a gluon, for example. Or they can exchange a gluon that the gluon itself emits another gluon that interacts with the other quark later. And it can also emit another one. And I start drawing all possible gluon diagrams. And so on. Okay? And now, how should we think of this outcome of drawing all these diagrams? What picture should we associate it? And we can draw here one more like this. Okay? So how do we think of this? Well, the outcome of all this, we can think that what we are doing is we have a string that is ending on a brain, another string on another brain, and we are summing over all string surfaces that go from one brain to the other. Okay, so we have some string surface going from one brain to the other. Okay? So in this case, this here would be an open string stretched between the quark and the antiquark, and by summing over all diagrams, I will be summing over all possible shapes of this string. And this is an example, like we said before, that in this ADS-CFT duality, for example, when we will try to translate this into a computation in string theory, what would this correspond to? It would correspond to saying that I have my path integral of my string, but the boundary conditions are that one open string ends here, and the other open string, and the other endpoint is separated by some distance r. And now I sum over all possible surfaces that go from one endpoint to the other endpoint. And which surfaces dominate if the tension is large? Well, the minimal surfaces, the one that go in the minimal direction. So this is an example where here we would integrate over surfaces x that are stretched between two lines and go from one line to the other. And when the tension is large, this would be e to the minus s of some minimal area times the tension, for the tension being very large. So this is an example where this side here, you see, if this is QCD, this side here is easy for lambda much smaller than 1, in which case the only graph we would have is a quark exchanging a gluon and nothing else. And this will be just Coulomb interaction. Just a quark and they exchange a gluon. It's 1 over x squared. It just gives the simplest possible thing. Whereas this diagram here, this thing here, you see it is just a geometrical problem. It's easy for the tension very large, which means lambda very large. Which means Tooth coupling very large. So this would be easy. Exactly in the opposite regime. Okay. So so this concludes, I think, for now at least a little bit these remarks.
When you connect the string theory, Larkin diagram, like, do we kind of guess the form by our pictorial intuition, or is there a kind of like equation that can make a little bit more manifest, like how this is?
Absolutely. So yeah, we will write precise equations like this theory with this Lagrangian is dual to this theory with this Lagrangian. But I'll get there tomorrow. Today it's just cartoons. Today is like going to the movies. Okay. So let's continue. Let me. So. Right. Okay. So I want to draw more pictures. I'm in the mood of drawing pictures. So, but do ask questions. I mean, okay. So let's now. So this just illustrates that this duality between open strings and closed strings is something that we should probably try to make use of. And in particular, you see that the fact that we can think of some processes, sometimes in terms of open strings and sometimes in terms of closed strings, it's already something quite remarkable, because the physics of closed strings are the physics of gravitons and gravity and whatnot. And the physics of open strings is the physics of gluons and gauge theories. So if we can make this is already kind of hinting at some correspondence between physics of the degrees of freedom of open strings, which are like gluons, gauge theories, and so on, and physics of the dynamics of closed strings, which are physics of gravity and backgrounds and studying quantum gravity in curved backgrounds and so on. So it's already kind of smelling something like what you probably heard about gauge gravity dualities and string gravity dualities and so on. So let's go on and explore this relation between two different descriptions. And let's consider the scattering of an electron by a heavy proton. So this is a proton. Okay, I mean, I don't need to say it's heavy compared to the electron. Of course, it's heavy. And then there is an electron. Okay? And I bended it to indicate that the electron is scattered by the proton, and the proton is like a classical probe. Now, how do we study the scattering of an electron by a proton? Okay? Well, we can start drawing all possible Feynman diagrams. The simplest one is just exchange a photon. And this gives rise to Coulomb interaction, for example. But there are other graphs. Plus, and then I draw other graphs where, say, after scattering, the electron radiates a photon. Or it can radiate a photon before scattering. Or it can have some correction to the string, to the vertex. Or that could be some vacuum polarization effects, and so on. And this is one way of studying the scattering of an electron by a proton. You just study all possible stories of the electron passing by the proton. Okay? These kind of processes, they have name, as we said. So this would be a vertex correction. This would be a vacuum polarization effect. This thing is called Bremsstrahlung. I don't know how to write. I also don't understand what I wrote, so I will write something with lots of consonants. I don't know. This is called Bremsstrahlung, and this would be one way to see how the electron gets deflected by the proton. Okay? Hey. Now, if you compute this, what you can read off is the potential generated by the proton and felt by the electron. And what the first graph will tell you is that to leading order you have a Coulomb interaction. But then there are corrections. For example, the other graphs would start giving you stuff like some alpha of 4 square root of m e to the minus 2 mass of the electron times the radius. I think 1 over mass electron times the radius to the 3/2 plus dot dot dot. Okay? Where this is called Uhlenbeck potential, I think, or something like that. And you start getting corrections to the potential of the electron. So then, you can also say differently. You can say that instead of having the proton, you think as the proton as generating some non-trivial background. This is a background. And then instead of doing Feynman diagrams, you just say, well, my electron moves in the background corresponding to this potential. And then I study the evolution of my electron in a non-trivial potential. So this would be description B of the same problem. And of course they are equivalent. So in one description, you say that the proton and the electron are both in flat space. And I sum over all interactions of one with the other. And in the other one, I say, no, there is no proton. I ignore the proton. There is instead just the electron moving in a non-trivial background. And this is equivalent. And these, of course, equivalent descriptions. And if you want, this is the essence of this open-closed string duality or of ADS CFT. It's trading interactions with the analog of this side would be the quantum field theory side, and the analog of that side would be the ADS side, as we will see. The analog of that side would be the analog of the closed string picture, and this would be the open string picture. But I think, morally speaking, I find this analogy to be a good one. So let me be a bit more explicit about why I'm saying that this is a good example. Now let's consider a similar situation in string theory, where instead of proton, we replace proton by something heavy. What's heavy? A stack of D branes. A stack of, say, D3 branes. And the electron is replaced by a probe closed string. Okay? And then what are we saying? We are saying that we have some brane, right? And we have some closed string that comes and interacts with the brane and then gets out. And what do I mean by that? I mean that it interacts with the brane, and, for example, it can produce two open strings here, and so on. Okay? And itself, it can have a hole in this surface, or it could be something different, something like this, where it would interact with the brane once, leave the brane, jump to the brane again, and leave. And itself, it could have a loop here, plus, etc. Okay? And now, we see what's happening. So you see that now you have different points of view. In one point of view, you think that the closed string was like a source that interacted with these open strings, and you have a description in terms of open strings. And then the closed string is another source. So it's like you put two sources on a theory of open strings, and you study what happens in terms of open strings. But from another point of view, you think in this direction, and you say there was a closed string passing by, and I threw closed strings at it. It was passing, and I shoot closed strings at the string. So there are two ways of describing it. So we have A, when we think in this direction, where we have the dynamics of open strings. So we have open strings in the brane. And then we think in the opposite direction, in the direction where we have a closed string and we emit the closed string in this vertical direction, Then instead, we would say that, no, I have my closed string moving around, but the effect of the brain was to generate some background, and I have no brain anymore, but I replaced the brain by some non-trivial background that describes the interaction of the closed string with the brain. And now I have a background. What are open strings on the brain? What do the open strings on the brain describe? Open strings on the brain describe young meals plus massive stuff. The string theory doesn't describe just massless modes, but also massive stuff, but in particular young meals. And what do we describe when we describe this gravity? That's gravity here. Here we are describing gravity plus massive stuff. And if you cross out the massive stuff, roughly, you start to see a correspondence between gravity and young meals. Okay? And this is at the essence of this ADS-CFT duality. So remember what we saw yesterday. What we said that these closed strings, if I think of them as some kind of vertex operators, then by putting many vertex operators, I could trade this by exponentiating the vertex operators and think that it was somehow deforming the background. Remember, I said put many vertex operators. In practice, morally speaking, you are deforming the background. Right? Because you are putting many vertex operators. This is equivalent to putting a vertex operator. And by putting many vertex operators, this is effectively exponentiating and deforming my action. So indeed, morally speaking, we think that we should be able to trade this interaction with the brain with changing the background for where the string moves. On the other hand, from this point of view, what we have, as I said, is a source interacting with open strings. So we are considering some source on the open strings. What could it be? Well, exactly what we drew there on top. That's exactly something like that. I put two operators, trace of f squared, trace of f squared. That's like a closed string source that I put, poof. And then I study its two-point function by studying interaction of open strings between the two. So this process could be exactly the picture associated to this trace f to the j with trace f to the j. I put two sources and then let the open strings, which are the gluons, the Young-Mills theory, tell me how it reacts to putting these two sources there. So this picture could be exactly the analog of the trace of f squared, whereas this picture would be related to interpreting the Feynman diagram picture in terms of a closed string moving in some non-trivial background that we would have to understand. This picture will be the analog of trying to understand what exactly do we mean by saying that we have a string theory and so on. Okay? This is the physical picture. So tomorrow we'll put formulas on it. I think today I'll stop earlier. Okay.